Chapter 5, the Periodic Law. Section 3, Electron Configuration and Periodic Properties. At the end of this video, I want you to be able to define atomic and ionic radii, ionization energy, electron affinity, and electronegativity. Compare the periodic trends for atomic radii, ionization energy, and electronegativity, and state the reasons for these variations. Define valence electrons and state how many are present in atoms of each main group element. And then compare the atomic radii, ionization energies, and electronegativities of the d block elements with those of the main group elements. So far, you have learned that the elements are arranged in the periodic table according to their atomic number, and that there is a rough correlation between the arrangement of the elements to their electron configurations. In this section, the relationship between the periodic law and electron configurations will be further explored. Atomic radii. Ideally, the size of an atom is defined by the edge of its orbital. However, this boundary is fuzzy and varies under different conditions. Therefore, to estimate the size of an atom, the conditions under which the atom exists must be specified. One way to express an atom's radius is to measure the distance between the nuclei of two identical atoms that are chemically bonded together, then divide this distance by 2. As illustrated in figure 5-2, atomic radius may be defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. Periodic trends. Like shown on figure 5-13, which is represented on page 141 of your text and will be on the next slide, figure 5.13 gives the atomic radii of the elements. Note that there is a gradual decrease in atomic radii across the second period from lithium to neon. The trend to smaller atoms across a period is caused by the increasing positive charge of the nucleus. As electrons add to S and P sublevels in the same energy level, they are gradually pulled closer to the more highly charged nucleus. This increased pull results in a decrease in the atomic radii. The attraction of the nucleus is somewhat offset by repulsion among the increased number of electrons in the same outer energy level. As a result, the difference in the radii between neighboring atoms in each period grows smaller. Group trends. Examine the atomic radii of the group 1 elements as seen in figure 5-13 on the screen now. Notice that the radii of the elements increase as you read down the group. As electrons occupy sublevels in successively higher main energy levels located farther from the nucleus, the sizes of the atoms increase. In general, the atomic radii of the main group elements increase down a group. Now examine the radii of group 13 elements. Although gallium, Ga, follows aluminum, Al, it has a slightly smaller atomic radius than does aluminum. This is because gallium, unlike aluminum, is preceded in its period by the 10 d block elements. The expected increase in gallium's radius caused by the failing of the fourth main energy level is outweighed by a shrinking of the electron cloud caused by a nuclear charge that is considerably higher than that of aluminum. Ionization energy. An electron can be removed from an atom if enough energy is supplied. Using A as a symbol for an atom of any element, the process can be represented as follows. A plus energy reacts to form A with a positive charge and an electron. The A with a positive charge represents an ion of element A with a single positive charge, referred to as a +1 ion. An ion is an atom or group of bonded atoms that has a positive or negative charge. Sodium, for example, forms the sodium +1 ion. Any process that results in the formation of an ion is referred to as ionization. To compare the ease with which atoms of different elements give up electrons, chemists compare ionization energies. The energy required to remove one electron from a neutral atom of an element is its ionization energy. Or, more specifically, first ionization energy. To avoid the influence of nearby atoms, measurements of ionization energies are made on isolated atoms in the gas phase. Figure 5-15 on the next slide and shown in your textbook on page 143 gives the first ionization energies for the elements in kilojoules per mole. Period trends. In figure 5-15 on the screen now, examine the ionization energies for the first and last elements in each period. You can see that in group 1 metals, have the lowest first ionization energies in the respective periods. Therefore, they lose electrons most easily. This ease of electron loss is a major reason for the high reactivity of group 1, or alkali, metals. The group 18 elements, the noble gases, have the highest ionization energies. They do not lose electrons easily. The low reactivity of noble gases is partly based on this difficulty of electron removal. In general, ionization energies of main group elements increase across each period. This increase is caused by increased nuclear charge. A higher charge more strongly attracts electrons in the same energy level. Increasing nuclear charge is responsible for both increasing ionization energy and decreasing radii across the periods. Note that, in general, nonmetals have higher ionization energies than metals do. In each period, the element of group 1 has the lowest ionization energy, and the element of group 18 has the highest ionization energy. Among the main group elements, ionization energies generally decrease down the group. Therefore, they are removed more easily. Also, as atomic number increases down a group, more electrons lie between the nucleus and the electrons in the highest occupied energy levels. This partly shields the outer electrons from the effect of the nuclear charge. Together, these influences overcome the attraction of the electrons to the increasing nuclear charge. With sufficient energy, moving on to removing electrons from positive ions. With sufficient energy, electrons can be removed from positive ions as well as from neutral atoms. The energy of removal of additional electrons from an atom is referred to as the second ionization energy, third ionization energy, and so on. Table 5-3 on screen now and on page 145 of your text shows the first 5 ionization energies for the elements of the first, second, and third periods. You can see that the second ionization energy is always higher than the first. The third is always higher than the second, and so on. This is because as electrons are removed from successive ionizations, fewer electrons remain within the atom to shield the attractive force of the nucleus. Thus, each successive electron removed from an ion feels an increasing, stronger effective nuclear charge. Effective nuclear charge is the nuclear charge minus the electron shielding. The first ionization energies in Table 5-3 show that removing a single electron from an atom of a group 18 element is more difficult than removing an electron from the atoms of other elements in the same period. This special stability of the noble gas configuration also applies to ions that have noble gas configurations. Notice in Table 5-3, again on screen now or on page 145 of your text, the large increases between the first and second ionization energies of lithium, Li, and between the second and third ionization energies of beryllium, Be. Even larger increases in ionization energy exist between the third and fourth ionizations of boron, B, and between the fourth and fifth ionization energies of carbon, C. In each case, the jump in ionization energy occurs when an ion assumes a noble gas configuration. For example, the removal of one electron from a lithium atom, again starting at helium 2s1, leaves the helium atom in the noble gas configuration. The removal of 4 electrons from a carbon atom, which starts at helium 2s2 2p2, also leaves the helium configuration in that carbon atom. Electron affinity. Neutral atoms can also acquire electrons. The energy change that occurs when an electron is acquired by a neutral atom is called the atom's electron affinity. Most atoms release energy when they acquire an electron. Release energy. In this book, the quantity of energy released is represented by a negative number. On the other hand, some atoms must be forced to gain an electron by the addition of energy. The quantity of energy absorbed is represented by a positive number. An ion produced in this way will be unstable and will lose the added electron spontaneously. Figure 5-17, represented on page 147 of your text and on screen now, shows the electron affinity in kilojoules per mole. Period trends. Too far. Period trends. Among the electrons of each period, the halogens, group 17, gain electrons most readily. This is indicated in figure 5-17, again on screen now, by the large negative values of the halogens' electron affinities. The ease with which each halogen atom gains electrons is a major reason for the high reactivities of group 17 elements. In general, as electrons add to the same p sublevel of atoms with increasing nuclear charge, electron affinities become more negative across each period within the p block. An exception to this trend occurs between groups 14 and 15. Compare the electron affinities of carbon, which is helium 2s2 2p2, and nitrogen, helium 2s2 2p3. Adding an electron to a carbon atom gives a half-filled p sublevel. This occurs much more easily than forcing an electron to pair with another electron in an orbital of the already half-filled p sublevel in that nitrogen atom. Group trends. Trends for electron affinity within groups are not as regular as trends for ionization energy. As a rule, the electrons add with greater difficulty down a group. This pattern is a result of two competing factors. The first is a slight increase in effective nuclear charge down a group, which increases electron affinities. The second is an increase in the atomic radius down a group, which decreases electron affinities. In general, the size effect predominates. But there are exceptions, especially among the heavy transition metals, which tend to be the same size or even decrease in radius down a group. Adding electrons to negative ions. For an isolated ion in the gas phase, it is always more difficult to add a second electron to an already negative ion. Therefore, second electron affinities are all positive. Certain p-block nonmetals tend to form negative ions that have noble gas configurations. The halogens do so by adding one electron. For example, chlorine has a configuration of neon 3s2 3p5. An atom of chlorine achieves the configuration of the noble gas argon by adding an electron to form the ion chlorine -1, chloride. Adding another electron is so difficult that chlorine -2 never occurs. Cl -2 never occurs. Atoms of group 16 elements are present in many compounds as -2 ions. For example, oxygen, which has a configuration of helium 2s2 2p4, achieves the configuration of the noble gas neon by adding 2 electrons to form O2-. Again, 2s2 2p6. Nitrogen achieves a neon configuration by adding 3 electrons to form the N3- ion. Ionic radii. Figure 5-19, shown on page 149 of your text, or the next slide, shows that the radii of some of the most common ions of the elements. Positive and negative ions have specific names. A positive ion is known as a cation. The formation of a cation by the loss of one or more electrons always leads to a decrease in the atomic radius before the removal of the highest energy electrons results in a smaller electron cloud. Also, the remaining electrons are drawn closer to the nucleus by an unbalanced positive charge. The negative ion is known as an anion. The formation of an anion by the addition of one or more electrons always leads to an increase in atomic radius. This is because the total positive charge of the nucleus remains unchanged, when an electron is added to an atom or an ion. So, the electrons are not drawn to the nucleus as strongly as they were before the addition of the extra electron. The electron cloud also spreads out because of the greater repulsion between the increased number of electrons. Period trends. Within each period of the periodic table, the metals at the left tend to form cations, and the nonmetals at the upper right tend to form anions. Ionic radii decrease across a period because the electron cloud shrinks due to the increasing negative charge acting on the electrons in the same main energy level. Starting with group 15, in which atoms assume stable noble gas configurations by gaining 3 electrons, anions are more common than cations. Anions become more common than cations once you get to group 15. Ionic radii decrease across each period for the elements in groups 15 through 18. The reasons for this trend are the same as the reason that cationic radii decrease from left to right across the period. Group trends. As they are in atoms, the outer electrons in both cations and anions are in higher energy levels as one reads down a group. Therefore, just as there is a gradual increase in atomic radii down a group, there is also a gradual increase in ionic radii. Valence electrons. Chemical compounds form because electrons are lost, gained, or shared between atoms. The electrons that interact in this matter are those in the highest energy levels. These are electrons most subject to the influence of nearby atoms or ions. The electrons available to be lost, gained, or shared in the formation of chemical compounds are referred to as valence electrons. Valence electrons are often located in incompletely filled main energy levels. For example, the electron lost from the 3s sublevel of sodium to form a sodium plus 1 is a valence electron. For the main group elements, the valence electrons are the electrons in the outmost s and p sublevels. The inner electrons are in filled energy levels and are held too tightly by the nucleus to be involved in compound formation. The group 1 and group 2 elements have 1 and 2 valence electrons respectively, as shown in table 5-4 on the screen now or on page 150 of your text. The elements in group 13 through 18 have a number of valence electrons equal to the group number minus 10. In some cases, both the s and p sublevel valence electrons of the p block elements are involved in compound formation. In other cases, only the electrons from the p sublevel are involved. Electronegativity. Valence electrons hold atoms together in chemical compounds. In many compounds, the negative charge of the valence electrons is concentrated closer to one atom than to another. This uneven concentration of charge has a significant effect on the chemical properties of a compound. It is therefore useful to have a measure of how strongly one atom attracts the electrons of another atom within a compound. Linus Pauling, one of America's most famous chemists, devised a scale of numerical values reflecting the tendency of an atom to attract electrons. Electronegativity is the measure of an ability of an atom in a chemical compound to attract electrons. The most electronegative element, fluorine, is arbitrarily assigned an electronegativity value of 4. Values of other elements are then calculated in relation to this value. As shown in figure 5-20 on screen now or on page 151 of your text, electronegativities tend to increase across a period, although there are exceptions. The alkali and alkaline earth metals are the least electronegative elements. In compounds, their atoms have a low attraction for electrons. Nitrogen, oxygen, and the halogens are the most electronegative elements. Their atoms attract electrons strongly in compounds. Electronegativities tend to either decrease down a group or remain about the same. The noble gases are unusual in that some of them do not form compounds and therefore cannot be assigned electronegativities. When a noble gas does form a compound, its electronegativity is rather high, similar to the values for the halogens. The combination of the period and group trends in electronegativity result in the highest values belonging to the elements in the upper right of the periodic table, and the lowest values belong to the elements in the lower left of the table. At this point, I hope that you can define atomic and ionic radii, ionization energy, electron affinity, and electronegativity. Compare the periodic trends of atomic radii, ionization energy, and electronegativity, and then state the reasons for these variations. Define valence electrons and state how many are present in atoms of each main group element. And then compare the atomic radii, ionization energies, and electronegativities of the d block elements with those of the main group elements.